Problem number 10. We have a rectangular box with a square base and no top. So I drew this picture right here for it. Let's see, what is there to be said about the volume needs to be 150 cubic centimeters. Okay, so we know we have that going on. Material for the base is expensive. It costs $6. I guess we want a strong base. But then material for the sides only costs $2 per square centimeter. How do we want to make this as cheaply as possible while having the volume be 150 centimeters. So how do we accomplish this? How do we go about figuring out how to accomplish this? We need some variables here. I'm going to label x as the side length of the base. It's a square, so both that and that are x. Going to let h be the height of the box here. So from a volume perspective, this says here 150 is equal to x squared times h. Okay, how about the cost? Okay, so the cost is going to be the bottom, the base has area x times x, and it costs $6, so 6 times x squared. Then each side has area x times h, and each side costs $2 per square centimeter, so 2 times x times h, and there's 4 sides, so we need to multiply this by 4. So 6x squared plus 8xh. This has 2 variables in it, x and h. We don't like that. We wish there was only 1 variable in it. So how do we do that? How do we make it so there's only 1 variable? We need to solve this for h in terms of x. So h is 150 over x squared. And then we take this, substitute in for x, and so our cost as a function of x is 6x squared plus 8x times 150 over x squared. So 6x squared, x and x squared cancel, so there's just an x downstairs, and 8 times 150 is going to be 1200, if my mental math is correct. Okay, so this is the function we want to optimize here. We want to minimize the c of x function. A word about the domain. The domain of this function is going to be from 0 to infinity. So any x value from strictly bigger than 0 and strictly less than infinity, any positive number is less than infinity here, is going to be allowed in our domain. Okay, so how do we go about minimizing this? We want to look for critical points. Let's take the derivative. 12x minus 1200 over x squared. So that equal to 0. Also for critical points, we have to think about, is the function undefined? But the only place where this is going to be undefined is if x is equal to 0, and that's not in our domain. So we can just go ahead and solve this. And let's see here. We can let's move this to the other side. So 12x is equal to 1200 over x squared. Let's move the x squared to the other side to get 12x cubed is equal to 1200. And divide both sides by 12. X cubed is equal to 100. So x is equal to the cube root of 100. Okay, and then if x is equal to the cube root of 100, h is 150 over x squared. So that would be 150 over 100 to the 2/3 power. So these are going to be the dimensions here, if I didn't make any mistakes. In terms of how do we go about showing that this actually genuinely does give a minimum, maybe the easiest way to do that is with the second derivative. The second derivative, so here's the first derivative of c. The second derivative would be 12 plus 2400 divided by x cubed. And this expression here is always positive. So our function, the graph for our function is always concave up. And so any critical point that's concave up is going to correspond to a minimum.